In this lecture, we're going to be examining the related effects known as interference and standing waves. Interference is when two waves are passing through the same point at the same time. Now, when we have two separate sources of waves, there might be a whole spectrum of points that are experiencing interference. On the screen, we see an example of two sources of waves. Imagine them as ripples in still water. And we have two kind of bullseye-like effects at the center of each of them. You can imagine that we have dropped stones in the water at the same time. And these ripples spread out. The circles represent the locations of the high points in the ripples, which means that midway between those circles, in the blank region midway between those circles, we must have low points. The black circles and the red circles represent special locations. You'll notice that the black circles occur where the peak of one wave intersects the peak of the other wave, whereas the red circles occur when the peak of one wave intersects a valley of the other wave, where the peak of one, the high point of one, is at the valley or the low point of the other. These are special points. The points where we have the black circles represent the locations where the waves combine to create a particularly high effect. And the red circles, because there's one high point added together with one low point, the red circles actually represent locations where it appears there is no effect whatsoever. The effect of one wave cancels out the effect of the other wave. This is, like I said, a snapshot. The actual situation evolves over time. But we can take a look at a picture. This is two ripples, sources of ripples. These prongs right here just dip in and out of a very shallow layer of water, and there's a light underneath so that you can see the ripples very clearly. And if you look closely, for instance, you'll see regions almost like straight lines where the ripples seem to not exist. It's almost like it's completely flat water. Not many regions, but you can look at regions where it looks like that there's nothing happening. That's like the red spots in the previous picture. On the other hand, you can also see regions where the peak of one is intersecting the peak of the other, and those represent the black spots in the picture. This is something that all of those places experience something called interference. But there are special circumstances known as constructive interference and destructive interference that are of particular interest. All of those places had a wave traveling through it from one source and a wave traveling through it from another source. So all of those places had interference, but some of those places had constructive interference, and some of those places had destructive interference. I also want to point out that this can be an evolving situation. There is also a time-based effect going on here. So we saw snapshots. It's quite possible that the locations of constructive and destructive interference will change a little bit over time, but we'll see that there's kind of a cyclical nature to it. In this animation that you're about to see, we have two sets of concentric circles. Right now, these two sets, which are identical, are overlaid over each other. But one of those sets of concentric circles is going to remain in place, and the other is going to start slowly moving to the right once I click this animation to begin. And so you see a time evolution taking place. Now, be careful. Don't be deceived by some of what you see. When we get the peak of one wave exactly crossing the peak of another wave, that's where we have a particularly high point in the waves. Where we get the peak of one wave crossing the valley of the other wave, that's where we get the equivalent of no effect whatsoever. But you can tell that there's something going on. You can almost see things splaying outwards. That's where the peak of one is actually meeting the peak of the other. So those regions where it kind of, you get this mirage-like effect when we get the peak of one overlapping the peak of the other, that actually represents a location where we get very high constructive interference. In constructive interference, the waves from the two different sources, which are presumably identical in terms of wavelength and frequency, overlap each other exactly. Now, I didn't show that in the upper graphic because if I showed the two waves overlapping each other exactly, you would see a single sinusoidal line. I wanted to demonstrate that there are two waves there. And the more these two waves overlap, the closer we have to perfectly constructive interference. The light red wave is the combined effect. The light red wave is basically the sum of each of the two separate waves. In the lower graphic, we see these two waves engaged in perfectly destructive interference. When one is at a peak, the other is at a valley. And the net effect is this horizontal red line, which is indicating there doesn't appear to be any effect at all. This is actually destructive interference. It represents perfect cancellation. So, perfectly constructive interference, the two waves combine to create a maximum possible amplitude. And in perfectly destructive interference, the two waves combine to create as near zero amplitude as possible. In between those extremes, well, we have a continuous spectrum of possibilities. And so I want to look at a more general approach rather than just limiting ourselves to perfectly constructive or perfectly destructive. And in order to handle this mathematically, we are stuck with having to consider the concept of phase shift. Phase shift can be thought of as the difference between the two waves. We think of perhaps a sine wave starting right at the origin and oscillating through, but what if the sine wave doesn't start at the origin? If it doesn't start at the origin, then it is phase shifted. And we can handle that mathematically. If you take a look in the lower right of the slide, you'll see this expression A sine kx minus omega t plus phi. Phi is called the phase shift. It's a measurement in radians. And with the appropriate value of phi, I can tell you exactly the displacement, the velocity, and the acceleration of this wave, even if it doesn't start exactly at the origin or exactly at a peak. Phi handles all of that stuff. And so what we need to do is we need to know how to be able to calculate phi, the phase shift between two separate waves, if we want to be able to determine the interference effects. How do we do that? We use the wave number K. You might recall from a previous lecture, I referred to K as a conversion factor. It allows us to convert from location to radians. So if I know the difference in location between the two waves, then I can determine the phase shift. If the difference in location between the two waves is delta x, then phi, the phase shift, is K times delta x, where K is the wave number, equal to 2 pi divided by the wavelength lambda. It doesn't matter if these sources are on a straight line relative to each other and an observer. All that we need to know is that the sources are identical and where the observer is relative to each of the two sources. Perhaps we have sources represented by the small black circles and we have an observer represented by the stick figure on the right. The wave has to travel from the upper source to the observer, and the second wave has to travel from the lower source to the observer. And of course, they have to meet each other at the same time for there to be an interference effect. But they can have different path lengths. One x1, the other x2. If I know x1 and x2, I just find the difference in those path lengths. I don't worry about direction. I just want a difference between the separate distances traveled by the waves. I want the path length difference, delta x. So the absolute value of x2 minus x1 gives me delta x. That's going to be in units of meters. It's a distance. And then I multiply it by this conversion factor, the wave number k, and that converts a distance into radians, and that's going to be the phase shift. So basically, the phase shift phi is equal to k times delta x, where delta x is the path length difference. Let's do an example. Sound in air at 20 degrees Celsius travels at 343 meters per second. Sound travels a little bit slower when the air is cooler. It travels a little bit faster when the air is warmer. But at 20 degrees Celsius, which is a comfortable room temperature, sound travels at 343 meters per second. Suppose I have two identical sources of sound. Both of them are at a frequency of 572 hertz. Both of them come from identical speakers, but the speakers are not identically located. And an observer is a different distance from one speaker than the other speaker. Let's say this observer, this listener, is 2.71 meters from one speaker and 2.55 meters from the other speaker. How do we calculate the phase shift in that circumstance? We need to figure out the wave number k. The path length difference is simply the difference between 2.71 and 2.55. But in order to get the radians, the phase shift phi, I need the wave number k. So we'll start by finding the wavelength. The wavelength is equal to the speed of propagation divided by the frequency. So 343 meters per second divided by 572 hertz gives me 0.6 meters for the wavelength. And now that I have the wavelength, I can get the wave number k. That's equal to 2 pi divided by the wavelength. And in this circumstance, that gives me a wave number of 10.48 radians per meter. And then we can find the phase shift. Phi is equal to k times the path length difference, x2 minus x1. So 2.71 minus 2.55, find that difference, multiply by 10.48, and we get a path length difference of 1.68 radians. Now, is this a reasonable answer? And yes, it is here. These are not shockingly odd numbers. The speed of sound is 343 meters per second. 572 hertz is a perfectly ordinary sound as far as human hearing is concerned. There's nothing weird about being 2.71 meters, what is that, about 9 or 10 feet away from one, and about 7.5 or 8 feet away from the other. Nothing odd about that. Is there a practical upper limit? And maybe not super practical, but any phase shift greater than about 4 pi radians is probably going to result in an effect that is negligible. Why would it be negligible? Because as the path length difference gets larger, phi gets larger in value. Well, if you are noticeably that much farther away from one source than the other source, if these two sources are identical, the sound from the nearer source is basically going to drown out the sound from the further source. In order for there to be an interesting effect, the sounds must have about the same volume by the time they reach your ear. Otherwise, the closer one just completely dominates the further one. So if there is an upper bound, I would say it's about 4 pi radians, which is equivalent to 2 full wavelengths. So if you get 4 pi radians, that's about 12 or 13 radians, probably the second source is too far away to be of much interest in the problem. When you hear a sound or see a source of light, what you are experiencing is the intensity. You might remember we brought up intensity in an earlier lecture as power divided by area. But there is also a relationship between the intensity that we experience and the amplitude of the wave that reaches us. And this is important, and so I bolded the phrase, I italicized the phrase, I should probably underline the phrase. We can show, it's beyond the scope of the course to show it, but I can show it to you if you're interested. We can show that the intensity of a source that we experience directly with our eyes or our ears is proportional to the square of the amplitude of the wave that is impacting us, whether it's a light wave or a sound wave or some other wave. The intensity is proportional to the square of the amplitude. Now suppose I have two separate waves that have the same wavelength, that have the same frequency, and have the same amplitude by the time they reach my ears, or to a good approximation, the same amplitude. The net effect that I experience, or that you experience, is the sum of the waves. We can, analytically, we can generate an equation that adds these two general wave equations together. One wave will have the equation amplitude times the sine of kx minus omega t, and the other can have A, the amplitude times the sine of kx minus omega t minus the phase shift phi. And it is possible to add these two equations together and come up with a single result. Nothing, when you analyze it, it is nothing that is as complicated as you might think. What we see on the right-hand side is the analytical sum of two separate but identical waves whose only difference is a phase shift phi. And we see that when we add these two together, we see 2 times A times the cosine of phi over 2 times the sine of kx minus omega t minus phi over 2. Let's interpret this. All of the spatial and temporal information is in the last part, sine of kx minus omega t minus phi over 2. In this spatial temporal part, k hasn't changed from the separate waves, and omega hasn't changed from the separate waves. What that means is the sound that you hear or the color of light that you see will remain the same. So if I have two separate sources of a sound at 500 hertz, the net sound that I hear is 500 hertz. It's going to be at exactly the same pitch. If I have two different sources of orange light, and the color of light reflects the wavelength and frequency of the light. If I have two separate sources of orange light, when they mix together, I'm going to get orange light. The wavelength doesn't change and the frequency doesn't change. But what does change is the phase shift of the combined wave compared to either of the separate waves. The combined wave has a phase shift that places it midway between the separate waves. The phenomenon is shown if we go back to this slide right here. We see the two separate waves that have a phase shift between them. The peak of the combined wave occurs midway between the peaks of the separate waves. And the wavelength of the combined wave is the same as the wavelength of either of the separate waves. So, same wavelength, same frequency. The location of the combined wave is at a phase shift exactly midway between the separate waves. Then we see this term in front of it, 2a cosine phi over 2. This is independent of location and time, 2a cosine phi over 2. So this combination is basically the amplitude of the combined wave. So we see the amplitude of the combined wave does depend upon the phase shift between them. If the phase shift between the two waves is 0, in other words, if these two waves are exactly one on top of the other, then we get the cosine of 0, which is 1, and we get that the amplitude of the combined wave is 2a. They've simply added together. On the other hand, if I want destructive interference, then I would have phi equal to pi radians. Now, pi radians is like 180 degrees. And it means that the two waves are exactly out of sync when they arrive at your ear or at your eye. And if they're exactly out of sync with each other, then what we have is the phenomenon shown in the lower part. These two waves that you see in the lower graphic are exactly out of phase with each other by half a wavelength. They are out of phase with each other by pi radians. They are out of phase with each other by 180 degrees. If my phase shift is pi radians, I'm taking the cosine of pi over 2, and the cosine of pi over 2 is 0. And so the amplitude of the combined wave is 0. And that's the situation of destructive interference. Given that the intensity is proportional to the square of the amplitude, we also see another interesting effect. In the situation of constructive interference, where phi is equal to 0, and the cosine of 0 is 1, I get that the amplitude of the wave is 2a, but the intensity is proportional to the square of the amplitude, which means that the intensity of the combined wave is 4 times the intensity of a single wave. I add two waves together, they are interfering constructively, and the combined wave is 4 times brighter, it is 4 times louder than either of the separate waves. So there's an interesting effect there if you can get this highly tuned information. This is not super relevant in sound, but this has some significant effects in dealing with light if we look at laser light pulses, where we can very easily, relatively speaking, control the wavelength. Think about this question here. If I have two identical interfering waves, and each of the separate waves has an intensity of I naught, I underscore 0, subscript 0. If these two waves interfere with each other and the phase shift between them is pi over 2 radians, what's going to be the intensity of the combined wave? Will it be 0 because of perfectly destructive interference? Would it be 4I naught because of perfectly constructive interference? Or would it be 2I naught because we are midway between those extremes? Think about it. Don't hesitate to ask questions. So that's some important parts of interference: constructive interference, destructive interference, interference in general. But there's an application of interference that is of substantial importance in quantum mechanics, which maybe you don't care about, and music, which maybe you do care about. And this phenomenon of standing waves occurs when I have a fixed end, and in fact when I basically have two fixed ends, so that the wave has to bounce off of this fixed end. When the wave bounces off a fixed end, the string, let's say, exerts a force on the fixed end exerts a force on the string. So if the string is pulling up on the fixed end, or trying to, the fixed end is pulling down on the string. And what happens, as we saw in an earlier lecture, is that there is going to be a reflection. So if I have a wave coming to the right, it's going to reflect off to the left. Most of the time, nothing's really going to happen. But sometimes, if the incoming wave comes in at just the right rate, the reflected wave can interfere with the incoming wave constructively. So most of the time, nothing happens, but at just the right frequency, something does happen. And that something that we are talking about is called standing waves. This demonstration right here includes the situation of standing waves. And the demonstrator right here is showing the apparatus. You see the long string, and there is a pulsing device on the left end that will cause the string to oscillate up and down, and it will send a pulse down the length of the string, and you can see that the far end is fixed. So he's going to start up the pulsation of the string, and you can see not much is happening. You know, there's certainly some vibrations, but nothing very compelling. But that's because he doesn't have it at just the right frequency. He's going to adjust it so that it is just at the right frequency for something interesting to happen. And we're right at about that location. This is what the standing waves look like. When you play the violin or any other stringed instrument, the piano, what they're trying to do is establish standing waves in the strings. And that's where you get the maximum effect. And it only occurs at a very particular frequency. So because it only occurs at a very particular frequency, you're only going to get a very particular note out of it. If you are away from that frequency, you're going to get a very junky-looking oscillatory wave, and you're not going to get much sound out of it at all. But if you get this standing wave effect, you get that intensity, and here we see it in slow motion. It's kind of interesting looking at it. You can see even some smaller wobbling in the string. That's its own interesting effect. Those of you who ever go into math and study what are called Fourier series will investigate that effect, but don't worry about it here. But it can only, this general effect of standing waves can only happen at very particular frequencies. Now he's pointing out locations where the string is pretty much absolutely still. Where the string is still, those are called nodes. So you typically have a node at each fixed end, and then one or more. Here we have a standing wave that just has a single hump to it. There's only a node on the left end and a node on the right end. The frequency of this wave, as we'll see, is 1/2 the frequency of the two-hump standing wave with which he started. Now, he can play around with it. The frequency of this is a bit lower than the two-hump situation. He can play around with it and get to a three-hump standing wave, and that's here. There's the two-hump standing wave, and he's going to make the frequency even higher. And there's the three-hump standing wave. So the frequency is even higher, and we get the standing wave effect. And we have a node on either end, and we have two nodes in the middle. And these nodes are pretty evenly separated from each other. So it's a very well-regulated effect. A little bit later, actually, let me wait. They'll show the slow motion. And so you can see that in slow motion, we get the actual oscillation of the string, each point oscillating up and down except at the nodes. And he's going to crank it up a little bit higher. And let's see what he gets. Oh, there was a 4. I think we saw the 5. And here is 1, 2, 3, 4, 5, 6. This is a 6-hump standing wave. And he has it oscillating at a pretty high frequency, to be honest. But it only occurs at very specific frequencies. It's not going to occur at any random frequency. There is a very specific, very predictable set of frequencies at which we see standing waves. How do we predict those? Well, let's do a little bit of an analysis. We saw situations of a one-hump standing wave, a two-hump standing wave, and a three-hump standing wave. And if I have identical strings of identical length, then the length of the string is capital L. In the one-hump standing wave, we basically see half of a full wavelength. The entire wavelength would be it oscillates up, and then it oscillates down, and returns back to equilibrium. The entire wavelength would be twice the length of the string. In the two-hump case, we see exactly one full wavelength, and so the wavelength is equal to the length of the string L. In the three-hump case, we see that a full wavelength occupies 2/3 of the entire length of the string. And what I did was I wrote down each wavelength in terms of in terms of 2L divided by a number. So in the one-hump case, the wavelength is 2L over 1. In the two-hump case, the wavelength is 2L over 2. In the three-hump case, the wavelength is 2L over 3. And by this point in time, you've probably picked up the pattern. If I have n humps, then the wavelength is going to be equal to 2L over n. It's also still true that the frequency is equal to the speed divided by the wavelength. V equals F lambda means F equals V over lambda. V is not changing. The propagation speed of a pulse traveling down the string doesn't significantly change. The tension really isn't changing, and certainly the mass per unit length isn't changing. So the speed of propagation isn't changing. And so what we get is that the nth frequency, the frequency of the nth hump, is equal to n times the propagation speed v divided by 2L. So if we know v and if we know the length of the string, we can predict the frequencies at which we get standing waves. Let's take a look at this example here. We have a violin string that by itself vibrates at a frequency of 440 hertz, which is the A4 note for those of you in the know. This is in its fundamental vibration. When we talk about the fundamental vibration in standing wave, that means n equals 1. Fundamental means n equals 1 in standing wave terminology. The length of the string is 32.9 centimeters long. Now, if you press down on the violin string at a different location, you are changing the effective length of the string. You're changing the value of L. And if you change the value of L, you're going to change the frequency. You're not changing really the tension in the string if you just clamp the finger firmly down on the string at a particular location. So you're not changing the tension, you're not changing the propagation speed, but you are changing the wavelength and you are changing the frequency. Apologies, the recording seemed to have stopped when I was right near the end of this. I don't feel like starting over. I'm just going to pick up where I left off, and so there's going to be a second part, brief part, to conclude this lecture. My apologies for the inconvenience. So by changing the location of your finger on the string and pressing down firmly, you're changing the length of the string, and you're going to change the frequency that's played. The string in question has a fundamental frequency of 440 hertz when you allow the entire length of the string, 32.9 centimeters. But if you want to change the frequency that you play on that string to 493.88 hertz, which is a B note, where should you place your finger? Well, let's understand this. the propagation speed of the wave doesn't change. We know the frequency when we allow the full 32.9 centimeters. We know the fundamental frequency. So that allows us to determine the speed of the propagation of the pulse in the string, 2 times L times S, and that's going to be equal to 289.52 meters per second. That propagation speed doesn't change. V is the same. But now, if I want to play a frequency of 493.88 hertz, I'm going to place my finger on the string, I'm going to clamp down firmly, and what must be the length of the string, and then we can figure out where I need to place my finger. The length of the playable portion of the string is going to be equal to V over 2F. But now, with this new F of 493.88 hertz, the propagation speed is still 289.52. I want the playable length of the string to be 0.29311 meters, whereas the unadorned length of the string is 0.329 meters. So, 32.9 centimeters minus 29.3 centimeters equals 3.6 centimeters. I need to place my finger 3.6 centimeters below the top of the string on the violin to get this new note. This is part of what goes into the determination of the location of the frets, F-R-E-T-S, on a stringed instrument. There are other complications that go along with it, but this is one of the major determinants. And you'll see that as the frets get closer and closer, as the frets descend down the neck of the violin, they get closer and closer together. And that's because the frequency is not the same as the length. The frequency and the length are inversely proportional to each other. Okay, that's the conclusion of this lecture. My apologies for the 2 parts. Bye-bye.